Ever wondered how FastMCP actually tracks and exposes your Python functions as AI-callable endpoints? You'll see exactly how the @MCP tool decorator transforms a simple add function into a registered tool that appears in the server's runtime registry. The test demonstrates FastMCP's core pattern. Decorate your function, then verify it exists with the correct name, all while following the official requirement of testing exactly one behavior per test.
Async def test tool registration. Test that tools are properly registered with the server. MCP, FastMCP, test server. @MCP, tool. Def add a int b, int. Return a +b. Tools equals MCP, list tools. Assert len tools equals 1. Assert tools 0, name equals add.
This demonstrates FastMCP's decorator pattern for creating AI-callable endpoints, where Python functions become registered tools while maintaining their native interface. The @MCP tool decorator preserves function names and type signatures, enabling runtime discovery through list tools, as shown by the test's verification of both tool count and name. The pattern's distinctive feature is how it maintains direct parity between your Python implementation and the exposed interface without requiring separate API definitions. The approach works by treating decorators as declarative registration markers that capture function metadata at definition time. When the test calls list tools, it validates that the framework has preserved the original function name, add, and registered exactly one tool, following FastMCP's requirement for self-contained test setups. This design keeps tool registration implicit while making the tools explicitly discoverable and verifiable through the server's introspection API. This pattern matters because it eliminates the traditional separation between implementation and interface definition in RPC systems. By making functions self-registering through decorators, you reduce manual configuration while gaining runtime verification capabilities. The test follows FastMCP's documented best practice of verifying exactly one behavior per test, demonstrating how the framework's design enables atomic validation of tool registration, a critical requirement for reliable AI integrations where endpoint discovery must precisely match implementation. Let's break it down line by line.
Async def test tool registration.
Defines an async test verifying FastMCP tool registration, following the official pattern of testing exactly one behavior per test. The async prefix is required because FastMCP's tool registration and execution are fundamentally asynchronous operations, matching the good atomic test example from the documentation. This test creates a self-contained FastMCP instance, registers a single tool using the @MCP tool decorator, then verifies the tool appears in the registry with the correct name, demonstrating the core pattern for creating AI-callable endpoints while maintaining explicit verification of each registration step.
Test that tools are properly registered with the server.
This docstring declares the test's single purpose, verifying that the @MCP tool decorator properly registers Python functions as AI-callable endpoints. It follows FastMCP's official pattern of testing exactly one behavior per test, ensuring the decorated add function appears in the server's tool registry with its original name preserved.
MCP, FastMCP, test server.
Creates a FastMCP instance for tool registration, using test server as the identifier. This is the container that will track all AI-callable endpoints, following FastMCP's pattern of self-contained test setup, where each test verifies exactly one behavior. The instance enables decorator-based registration while maintaining explicit tool naming, as shown by the subsequent tool 0, name equals add assertion.
@MCP tool. def add a int b, int.
The @MCP tool decorator registers this function as an AI-callable endpoint with FastMCP. Type hints define the tool's schema, while the decorator handles registration, transforming Python functions into remotely executable tools that maintain their original names. This follows FastMCP's pattern of self-contained tests, where each test verifies exactly one behavior.
Return a plus b.
This is the tool's business logic implementation that FastMCP will expose as an AI-callable endpoint. The simple arithmetic operation demonstrates the minimal implementation pattern, where the decorator handles registration, while the function body contains the actual computation. The test verifies this exact behavior, that the decorated function appears in the tool registry with its original name preserved.
Tools equals MCP, list tools.
This retrieves all registered tools from the FastMCP instance, verifying that @MCP tool decorator successfully exposed the add function as an AI-callable endpoint. The test follows FastMCP's pattern of checking exactly one behavior per test, here confirming the tool name matches the decorated function.
Assert len tools equals 1.
This assertion verifies that @MCP tool decorator successfully registered exactly one AI-callable endpoint, confirming the decorator transformed the Python function into a discoverable tool. It follows FastMCP's atomic test pattern by checking a single behavior. That list tools returns the expected count after registration. The test matches the official good atomic test example, ensuring each test verifies exactly one behavior with self-contained setup.
Assert tool 0, name equals add.
This assertion confirms the decorator preserved the function name during tool registration. It validates that @MCP tool correctly maps the Python function add to an AI-callable endpoint with identical naming, following FastMCP's requirement that tool names default to their function names. This matches the official test pattern of verifying exactly one behavior per test. FastMCP tool registration. The @MCP tool decorator exposes Python functions as AI-callable endpoints while preserving their names in the server registry, exactly as shown by tool 0, name equals add. This test follows the official pattern of verifying exactly one behavior tool registration, with self-contained setup and atomic assertions. Master this pattern to build reliable FastMCP servers that match the documented, good, atomic test standard.
The function that gains a decorator loses its local boundary.